Just do some of those. Just like you did you create the object in the map? The array object in the map.
那个右面的红色的钮不行，录像。
Two ways to do it. So
那我现在开始录了。
that's the way I did it first. Geocation. Really, what you're supposed to do is create an array of countries. We use that as the map solution. I wouldn't make this CSVs. You're linking. You go to Topo, you go to Geo, and you go to Geo, and then you link Geo to CSV. And it's kind of there's a form of line. This is the thing. GeoJSON has a tag, a 3-letter abbreviation ID.
There was something you can replace it with.
Population has a tag. So that's how you link. If you look at the top of that file, map. Look at the map, JavaScript, look at the top. That's the object's already there. That's the object you're going to create an array of. So you'll see that whatever parameters it has, you'll know. You just got to figure out how to get those things and then create arrays for all the countries. And the good thing is you can do it for all the countries in Geo. Because Geo has like 200. This is the trick. Geo's going to have like 253 or something. Something like that. Population in regions, some of them don't have regions. So we got to do a default. It's countries. Those are style for countries. So it doesn't have a region, you got to do this check. Does it have a region? If not, just call countries. Region countries. And then have to do style. It's default. It's about 10 hours trying to figure out what is this. This front end stuff, if there's like a front end visualization classes on front end stuff.
Is there like a tree that builds like dogs?
Yeah. So that was skip a bunch and now we're doing this.
That is hard project
Yeah, I don't like almost like it's kind of like front end, but back then it's more like, yeah, hey, you change one word, go reload the eventually, one of the Alright, let's get started. It's called
I don't have to
So,
take it.
about the project, today is the due date, and the deadline will be 11 o'clock in the evening, at night. And so, I see there's still one group who still doesn't have the correct tracking on the tracking page. So that group, I think they may have public repository. That's why we didn't add it to our tracking. So if you are a member of that group, please make sure your repository is private before the deadline so that you can come to your submission. Your latest commit as a submission. Okay. So let's get to the lecture. Last time we talked about access methods and different access paths like key file, solid file, indexes, and in particular for B-tree indexes, you have a lot of things to consider, like do you have a single key or a composite key, or is it cluster or unclustered, right? So for key file and solid file, that's about it. So that's the best you can get. So for the next couple lectures, we'll talk about different indexes in details. So the first part would be the B-tree index or B plus tree indexes. That would be the main focus of this lecture and probably the next lecture. Okay. So let's do a quick recap over last lecture. So we talked about how do we what the indexes are. Basically, an index is a collection of data entries, and a data entry is basically a key, a search key, and a pointer to some location in your key file. Or alternatively, you have three alternatives, right? You could have a key and the data record itself in the data entry. You could also have a key and a pointer, or a key and a list of pointers. But we've said there are trade-offs between among these three different options. Basically, so for the first one, you could end up with variable length data entries, but your index is implicitly clustered. That's good for like I/O, right? You get sequential I/O for that. For the second alternative, it's the most common one because the data entries are typically small, especially if the RIDs are actually very small in this sense. And but however, whether your tree is clustered or unclustered, it depends on how you store those data records in your key file, right? For the third option, I think it's the most impractical one because you get a variable length of this list, and it's not very uncommon for you to have a very huge group in your table. Like you can have a very skewed table where almost everybody has a GPA of greater than 3.0, but other people, like very few people, get something lower, right? If this is a graduate student database, right? So in that way, if your key is actually the bracket, then you get a really long list in your database, and that could span multiple pages, which causes a lot of trouble to your space management, right? But however, these data entry choices are actually orthogonal to the problem of how you do indexing. Like it's orthogonal to whether you use B-tree or hash maps, right? And the good thing about tree structure indexing basically is that it supports a wider range of queries than hash-based indexes. Like you can support range searches and equality searches, and sometimes inequality searches as well, because you can basically like you can exclude some part of your answer. Like if you are just doing the count, and you know the total number is n, and you can do a like inverse of your query, like just check for those that satisfy the equality condition, and count how many there are, and subtract that from n, right? Before we go into the details of B plus tree, we will first talk about something called ISAM. It's a very old indexing technique. ISAM stands for index, sequential access method. So this is really old, but however, up until I think 2010 or sometime later, MySQL only supports this, right? I don't think it's 2010, but somewhere after 2000. Initially, MySQL only supports a storage engine called MyISAM, and later they introduced the InnoDB, which is more like better in the sense it's more like more than database storage. Yeah. So before we go into the B plus tree, we will first talk a simpler version of that, the ISAM. So a little note of caution. So as I said, ISM is a really old-fashioned data structure. So usually you do not have any reason to use ISAM in today's applications. But it's a good place to start. Like from here, you will learn some like how to construct a tree structure index, and also a lot of ideas also copy over from ISM to B plus tree. So basically, there are trade-offs between the ISM and B plus trees. Okay. So let's first see something new. So this is called index entries. So what are index entries? An index entry is something similar to a data entry. Is that it's actually a pair, like this. So basically, you have a key as the first component of the pair, then a page ID as the second component, which acts as a pointer. So what it actually so how it works is that once you try to find some key in this through this index entry, you find where that key is located in. Like, so for example, suppose this is K1 and this is K2. Of course, K1 is going to be smaller than or equal to K2, right? So if you are searching for some key like K star, such star, K1 is smaller than or equal to K star, and it's smaller than or equal to K2. Then you know this key is probably under this pointer. Okay? Then you can just follow this pointer to another page to like do a search, right? So I'll talk about a little bit caveat here a little bit later. But let's see how actually we construct these index entries and how we use them in ISAM. So the basic idea is that initially you have a bunch of key pages like this. So basically this is the data file with the key pages. And at one level above here, you can build a bunch of data entries. As we talked about in the index, it's basically a collection of data entries. So basically, in each of this page, you have a bunch of data entries, and they are sorted in this level. So let's just say K1 is smaller than or equal to K2 and K3, and so on. And you know this K4 is smaller than or equal to any key on this K2, okay, and so on and so forth. So basically, this level is sorted, and you have one data entry for each record. So this is actually alternative 2. Okay. So in each of these data entry, you have a key of that particular record and a RID, a pointer to the actual key. So given this sorted file, so basically you can think of these leaf pages as a sequential region in your file. So then they are basically a sorted file. So when you are trying to do a search based on this key, you can do a binary search, right? So what's the cost of this binary search? It's gonna be log 2 n over b, right? So typically we think the log factor are small, but since you have a very small number here, so that means if this n over b goes too large, this is still going to be a lot of items, right? So suppose your n over b is 2 to the 20, then log 2 to the 20 will be 20. So for each search, you're going to pay 20 items, which is a lot, right? So suppose each of them takes you like 10 milliseconds, then this is 200 milliseconds, right? So it's really expensive. So how can you speed up this? The idea is that you can create an index file over the data entries, and you add one level of indirection again. So like this. So basically, you have a bunch of data entries which has keys, right? And you want to search. So suppose you are given a key, k star, and you want to search where this k star might be in these pages. You want to search for that page. So the way you do that, you add another level of sorted file, and in this sorted file, you have the key for the I think for the largest element. It's actually like this. So if you have a k prime 1 here, and you have a left pointer to the left of this k prime 1, it's going to point to the first page, and the second pointer is pointing to the left page 2. Then that means basically every key in the left page is going to be smaller than or equal to k prime 1. Every key in the leaf page 2 is going to be larger than or equal to k prime 1. Okay? Then if you know this, you can do a binary search for the very first k prime something. For the first, you can search for the first k prime something, say I, that is greater than or equal to k star, the very first one of that. Then you'll know that anything that contains k star will be at least after the right pointer of this ki star ki prime, right? So if you find index entry here, it's k prime I, and you have a pointer here. Since k star is greater than or this is wrong. The other way around. So try to find the very first one that is smaller than or equal to. Okay, so that you know that k star is greater than or equal to this ki prime, and this is the first such key. Okay, then you know anything before this such key is not going to be equal to k star, and anything that will equal to k star is going to be starting from this page, being somewhere that's starting from this page. Okay, so that's how you do the search. So does that make sense?
Yes. So what you know is that k star is greater than some other k.
Right. So you find this is a little bit easier. So let's suppose we do not have any duplicates in the tree. Then it's a little bit easier. So basically, you are going to find the k prime that's smaller than or equal to k star. Okay, and it is guaranteed there's only one of them. One of them that is the last one, the largest one. Okay, so if you find, so suppose this is 1, this is 3, and this is 6. okay? And you are searching for a 6. Of course, everything here satisfies the condition of k prime smaller than or equal to k star, right? But this is the largest one or the rightmost one, okay? And you find that one. Once you find that one, you know everything before this key is not going to be, so basically your k star is not going to be in anything that's on the left of this key. Why is that? Because everything before this is smaller than this k prime. Make sense? Yeah. So the way we define an index entry is like this. So if you have k prime and a pointer here, so basically that means everything in the page that's pointed by this pointer is going to be so suppose you have an x here. X is going to be greater than or equal to k prime, and anything that's before that is going to be smaller than this k prime. So anything before that is going to be smaller than this k prime. So if you search for the largest such key, you know if this k star ever exists, it's going to be in your right pointer. Okay? And what if you do not find any of this key? So every key is larger than your k star. Then it's in the leftmost pointer, right? This is how you do the search. Okay? But there are some caveats about this. Like we're assuming this only have unique keys. But what if you do not have unique keys? You have duplicate keys. Okay? Then some bad thing can happen here. Like so, suppose it's like this. So you have one here and one here. That basically means this leaf page are all one, right? Because everything in the right is going to be larger than or equal to the key, the k prime 2, right? Everything on the left is going to be smaller than or equal to this k prime 2. Notice that this time we are using smaller than or equal to instead of smaller than, because we cannot guarantee that the same key won't span multiple pages, right? Since we have different keys. Okay? Then in this case, when you are doing this search, you must search multiple pages. Like when you search for, say, you are search for 1. What you are gonna do is that you are not trying to find the largest one. That's the largest one ki prime is smaller than or equal to k star. If you are doing that, you are gonna end up with this one. Suppose the next one is 3. Okay, you are gonna end up with this one. Then you are gonna miss a bunch of ones out here and here. So what you are going to do is that you try to find the largest ki prime such that it is smaller than k star. So in this case, you do not find that key. That's implicitly means it's this entry here. The very first entry does not have a key because it's implicitly minus infinity. So that means this actually the very first entry, this k0 prime, is smaller than your k star. Okay? Then you follow the right link of this entry, that is the leftmost entry here, and try to search for ones out there. And it is guaranteed that every one is going to be at least in this page or in some page after this page. Make sense? Any questions?
So, I'm still not sure how k prime is related to k.
Alright.
Are they in sequential order?
Yeah. So
So, did you count k1, k2, k3 to k prime 1?
no. Basically everything in this level is sorted. This level is sorted, but they do not have definite sort order between them. Like you cannot count k1, k2, k prime 3. That's not possible. Right? The only relation between this layer and this level is that So K2 is going to be smaller than or equal to K1 prime. K3 is going to be larger than or equal to K1 prime. So then you have some order, but that's not important here.
So is that arrow explicitly going between K2 and K3?
No. Oh, I'm sorry. I was wrong. I was confused. Sorry. This doesn't mean that. Yeah. This is the same page. Yeah. Actually, it means something like this. So basically, the largest one is K4 here, right, in the first page. And you will have some K5 in the second page. That's the smallest one of the second page. So that will mean this K1 prime is going to be larger than any key in this page. That means K1 prime is larger than or equal to K4.
And it goes in between K2 and K3.
No, it doesn't go between. This pointer points to this entire page. Doesn't go point to this like gap here. It doesn't mean that. This pointer is pointing to this whole page. Alright? So the only meaning of that is that K1 prime is going to be larger than or equal to any key in this page. But it doesn't have any relation like between K1 prime and K2. It just means K1 prime is going to be larger than or equal to K2, but no other.
And the K primes only point to other keys in your quotation pages?
No, K prime doesn't point to the keys. They point to the pages, this whole page. So basically point to the 4 keys here. Okay. Does that make sense?
So if the keys pointing to pages and this page is pointing to other pages.
Right. Basically, your pointers are always going to point to pages, except for the data entries. So the data entries are actually points to the records themselves. But everything in the index layer is going to point to the pages.
Pages in memory.
Sorry?
Pages in memory, right?
No, pages are on disk. So they are
the
basically
second layer then is in on disk.
Right, everything is on disk. So these pointers are page IDs, and these pointers are record IDs. Okay. So these pointers are pointers to records, and these pointers are pointers to pages. That's what's going to happen. Okay. Yeah. So let's take that offline if you have further questions about this. Okay. So yeah. So the idea of the entire search process is to do a binary search on the first layer of this index entries and find a suitable key for that, like satisfy this condition, right? Search for the very last key that satisfies this condition and follow the right link of that key and start your search of K star over there. If you do not have any duplicates, then the thing is a little bit easier. Then you just find the very first key. You try to find the very first key that is smaller than or equal to, sorry, the very last key that is smaller than or equal to K star. Okay. Then you follow the right link and you get the exact one key of them, or you do not find it at all. Okay. I'll give you some examples about the search later. So let's see some concrete examples so that it is clearer to you. Okay. Yeah. So still, there's another problem. So basically, here you have a bunch of data pages, and then the data pages are not shown here. Actually, they are here. Okay. These are data pages. Then you have a bunch of leaf pages which contains data entries. These data entries are going to point to the data page. The records in the data pages. Then you have one additional layer here, which contains index entries. Then, whenever you do a search, you still need to search for the correct index entry in this level, in this particular level. Then the thing is going to happen is that what if you have too many index entries so that your binary search is still very slow? Then you can reuse this idea to build index entries on top of index entries. That is to say, you build another level of indirections like here, which still contains sorted keys, and you have a bunch of index entries that's going to point to each of the page in the next level. Then, when you do a search, you first do a binary search in the this view level, then follow the correct link to the next level. Then since you are at the next level, you can just follow a correct link in that page to go to the correct data entry, right? Then once you are at the data entry, you go from the record ID link to the actual data record, okay? And then this still can be hidden, right? Then you apply this idea recursively, and until you end up with one single node out here. This is one single page that contains a bunch of index entries that's pointing to its next level. Okay, and this way you get a tree. Yep.
Does this affect the timing on insertion and delete?
Right. Yes.
It does.
Yes, it does.
So is there some payoff to not go to one node and maybe have it just a little bit of a larger?
Yeah. So this way, of course, you're getting some overhead, but we will show that this should not be very large. So, okay. Okay. So here's an example of this. Suppose this is your ISA entry, and this level are data entries. Data entries. They are not data records. They are just data entries. Okay. And this is the level one. Sorry, one level above the data entry. They are index entries. And this is also the index entries. Okay. So suppose each of your node can hold two complete entries, two complete data entries or index entries, and one additional pointer. So basically, each of the index node is going to have 3 pointers and 2 keys, and each of your data entry node is going to have, or leaf node is going to have two data entries. That's what's happening here. And the values shown here are the keys. Okay, and we have shown you the pointers. So basically, this is the pointer pointing to this page here, right? And this pointer is gonna, this pointer is the pointer pointing to this page. Okay. Then, of course, in this data entries, there are gonna be pointers actually pointing to the actual data records in the heap file subrecords. Okay. So let's see how we do search here. So suppose we want to search for 37. How do we do that? We start from the root here, and we search for the very last key such that it is smaller than 37. So we want to find some k1 that is smaller than 37, right? And we just look at every value here. This is a 40, it's not smaller than 37, and you know that. Everything that basically means the very first entry here is the only one that satisfies this condition. Okay, this is implicitly a minus infinity here. So this is your the entry that satisfies your condition. Then you follow the right link of this because you know everything after this link is going to be larger than 37, and everything that's before this link is going to be smaller than 37. So that means if you follow this link, you are going to find 37, following this particular chain. Then you end up with this page, the second page here, and you do the same. You search for the last K2, such that K2 is smaller than 37 again, right? So once you find that, it's gonna be right here. So it's gonna be this 33 here, and you follow the right link of that, and you end up with, in the leaf level. And in the leaf level, you just search for the key itself. So it's 37 here. Then you know where this 37 key is, right? And as the last step, you follow the link to the of RID to to the actual data record. That means basically you find the record with the key 37 here. Okay, that's how you do this. So what if we are searching for some key that's non-existent? So what if you are searching for 38? Okay. Yeah. This should be smaller than. Yeah, smaller than. You find a 38 here. So if you are trying to find 38, of course you are still going to end up with the very first entry here and follow the link here, right? The first link. So you still find the very first link here and follow that link, end up with this node. Then this is a 38. You find the last key that satisfies this condition. So it's right here. Then you follow the link and end up with this link page and search for that 38. Since the 38 is not in this level, you know that this 38 is not possible to be in anywhere in your tree, right? Because basically everything after that is going to be larger than 38 because of the construction. Make sense? Yeah, I made some. I think I've been making some mistakes about this sign here. This is really tricky. So yeah, it really depends on how you define your data structure. Okay, really depends on how you define this link is gonna be smaller than or equal to. That means basically everything is everything here smaller than or equal to this key here, or is it strictly smaller than that? That makes a lot of difference, right? In your search strategy. So in your lab, you are gonna implement something like this. So make sure you understand which alternative you are using, like how you define this key here. Then it will make some difference. Okay. So any questions about the search process?
So,
Yes.
each of these be a longer array does not to be.
No, they are fixed size because these are basically each of these square here is a page. A page only have a fixed size and it can only contain a limited number of data entries or index entries. Okay, so basically they are fixed size. Yeah.
So each of these references one page. Each number on there points to one page.
Points to one record, not one page. Everything that's up, so these links are pointers to pages, and these links are pointers to records. Okay, they are different. These are data entries. These are the things at the bottom level are data entries. The things at the upper level are index entries. They are totally different data structures. So the way actually, so why is this ISAM called so index sequential access method? That's because the way how it is constructed. Actually, initially you have a bunch of data pages here. So these data pages are actually you can think of them as the data records. Sorry, data entries. No, sorry, the key pages. Sorry. These are the key pages. Actually, they contain the actual records there, and they are actually sorted. So initially they are sorted. So that means you actually have the cluster index here, and the way you build things is that you create one data entry for each of these data entries. For each of these data records here, and store them sequentially. Then you build on top of that, build another level of indirection, and also store them sequentially. So basically, these are data entries. Then it's going to be index entries of one level above, right? Let's say just level 1, then level 2, and so on. Alright? Then you have these overflow pages. What are these for? So once you are gonna if you are gonna insert something here, say you are gonna insert 28 here. What you are gonna do is that you are not going to, since you do not have any space here, you have to create a new page and use that as an overflow page here to store that at 28 here. So the way you do that is that basically you can try to say we are inserting 23 here. What we do is that we first find the location for this 23 using the very same method we talked before. So you search for a k1 that's greater than or equal to 20, sorry, smaller than or equal to 23, and search for the very last one, okay, and you end up with here, and you follow this link. Then you search for k2 that is smaller than or equal to 23, and it's going to be this one, right, the 20 here. Then you follow this link, and you know if the 23 ever exists in your tree, it should be in this page, but it's not there, right? That's why you're inserting that, and it's this page is already full. That basically means you do not have any space for this 23. What you do? So what you're gonna do is that you create a new page and put 23 over there. Then add an additional link somewhere from this page to this to the additional page. Then this is called an overflow page. So that means, so since your leaf pages that cannot like store everything there, so that's why you add something that make those overflowing entries into this overflowing chain. Okay, and when you do some search, if you find there is an overflow page, you not only need to search for things in the leaf page, you also need to search the entire chain of these overflow pages. Okay. So if you do this again and again and again, you end up with something like this. So this is the same we talked before, like your 23 is going to end up in this overflow page, and if you insert 48, 41, 42, then they are all going to end up in this page, and there's no room for them, so you create multiple overflowing pages and form that as a chain. Okay. Then suppose in this particular ISM tree, I'm searching for 48. What I'm going to do is that we first follow this link, then we follow this link, and we end up with something that has overflowing pages. So then what we are going to do is that we need to search for every overflow pages until we find the match. Okay, so we look at here and here, no match. Then we follow this link to the overflow page, and we find the match here. And that means we found this 48 entry. What if we are searching for 45? Okay, then you still follow the same links and end up with here. Then since it has overflow pages and 45 is not in the leaf page here, you go to the next overflow page and search for 45 here. Still not there, then you go to the next until you deplete all the overflow pages. And at that point, if you still don't find 45, that basically means 45 is not in the field. Okay, make sense? And what happens when we delete things? So suppose we are going to delete 42, 51, and 97 from the tree. So what's going to happen is that, so deletion is basically another search and a deletion operation. So what you do is that, so you find the pointer for 42, that's here. You follow this pointer for 42, then follow this pointer for 42 as well, right? And you end up with a leaf page that with overflow pages. So you search through all the overflow pages and find 42 is here. Alright? Follow these links. And then you remove this 42. Since this overflow page is already empty, you can uplink you can scratch the entire overflow because it's already empty. Okay, that's how you delete 42. Then when you delete 51, what's going to happen is that you first follow, then you follow this link for 51, then you follow this link for 51, okay? Yeah, it's here. Yeah, for 51. Then you find a match over here, then you just remove this data entry. But since this is a leaf page, even if it's empty, you do not remove this leaf page, just leave it empty. Okay? But of course, here are still things, so you do not remove anything, just remove the data entry itself. Okay? When you delete 97, it's the same. You follow this link and this link, and remove the 97 here. Okay? Okay, one more question. So what if we are removing 55 here? What's going to happen? We end up with this page, and we find the 55, and we remove this data entry. Now this leaf page is empty. As I said, you do not remove a leaf page. You just leave it there, okay, with a bunch of, even if it is an empty page. And when you do these deletions, you do not actually modify anything in the index pages. So they are static. In this sense, they are static. You do not change anything over there. Okay. So about ISAM is that next leaf page pointers here. So suppose you are doing a range query, like find all the data entries that is greater than or equal to 20. What do? You first find the first key that is greater than or equal to 20, which is here, right? And then you scan through all the leaf pages that is after this page, the first page you found. Okay, but still you do not need to actually maintain these right pointers for these leaf pages. Why is that? Any ideas why we do not need to maintain any of these next leaf page pointers? Any ideas?
The container the next level up, I don't know if you can go back up.
No, you should not go back up. Yeah, the reason lies in this, because all the pages are actually stored consecutively in one level. So when you construct this, these are still the data entries. So the data entries are sorted and stored sequentially in this grid. Okay. So since they are sequential, you can just read the page with the one larger page ID, and you find that page. So that's why in ISAM you never maintain this next leaf page pointers. Okay, you do not need them because these pages are sequential of this. Yep. So as you see, one problem with ISM tree is that once you have a lot of insertion and deletion, this tree can grow really fast. Suppose initially your data is roughly uniformly distributed in 1 to 10. Okay, then probably this is just a bunch of 1, 3, 5, 7, right? And basically under each of these links, you have roughly the same amount of tuples. But as time grows, maybe you are inserting too many 5 and 7 here, something between 5 and 7 here. Then under this link, you have too many tuples over there. That means somewhere under that, in the leaf pages, you are going to end up with a very long overflow chain. Okay, and if you delete too much from like 1, 2, 3, that means basically you are going to have a lot of empty leaf pages out there. Then when you do a search, this is bad because when you search for something that's between 5 and 7, you are essentially doing a linear scan over a very long list of pages. Okay? And also, because these are overflow pages, they are not necessarily stored sequentially in your file. So that means a lot of random IOs as well. So that could be really bad. So that actually leads to a better data structure. So B plus tree is something actually looks very similar to this ISAM here, but it's dynamically maintained. So that basically means not only your data pages, the leaf pages can be changed. You also maintain, change the distribution in your index pages. When you do some insertion or deletion, you also change those keys in your index entries, so that this tree is still balanced. Okay. So the way we do this is that we will still use the very similar data structure here. Basically, each of these index entries is still going to be a pair of key and a page pointer, right? And the leftmost still doesn't have any key because it's implicit. If it's the leftmost, it's implicitly negative infinity. If it's somewhere here, then it's implicitly the previous key in the previous page. Okay, and so basically this basically share the same data structure. And if you look at this, the leaf pages, the whole data structure looks exactly the same as a perfect ISAM tree, right? The only difference is that these leaf pages does not have, these leaf pages do not have any overflow pages. So when you are insert something, we will talk about how you actually can split one leaf page into two, so that you have some room for new updates. Okay. And another thing is that we do not necessarily, since we are not allocating this in advance, we can create new pages. So these leaf pages are not necessarily stored sequentially in your file. They can be anywhere. So that's why in the last level, we now maintain both the next leaf page link and the left leaf page link. Okay, they kind of help you when you have non-unique keys. Like your one key can span multiple pages, then you need to do linear scan over the leaf pages for some reason, or you are doing range search so that you're say greater than or equal to 5, then your keys are gonna be stored in multiple leaf pages. You need to scan all the way to them. Okay, so basically these links have serves that purpose. Okay, so let's see an example here. Yeah. So the definition of the index entry is still the same. So basically, if you have a 17 here, that means every key on the left is smaller than or equal to 17, and everything on the right is greater than 17. Of course, one thing to say is that these definitions are not necessarily the only way to do that. You can also define this is smaller than and this is greater than or equal to, right? You can also do both non-strict comparison, like everything on the left is smaller than or equal to this, and everything is 17, and everything on the right is greater than or equal to 17, depending on whether you have unique keys and which flavor you prefer. But for the example here, we'll assume we have only unique keys. So basically, we have unique keys. So we have unique keys. Sorry. So we have unique keys, and we assume that everything on the left is a non-strict comparison, and everything on the right satisfies a strict comparison. Okay. Then, basically, we still end up with the same kind of data structure. And there's one additional requirement for this index entries and data entries. We require that they are at least half occupied. That means you cannot say each of them have 4 entries, right? You cannot have less than 2 entries because half of 4 is 2. Okay, so you that applies to all the index pages and data pages except for the root, because sometimes if you just have one tuple there, your root is only going to have 1 link, right? So that actually cannot be enforced. But other than that, everything should be at least half occupied. That means you should have entries. So your number of entries should be at least half of the capacity of your pages. Okay. Then suppose we are trying to find 28. We just do the same as we do in ISAM. You find the very first key that is smaller than. Sorry, the very last key that is smaller than 28, and yeah, this way you should do. So this is a little bit different. So if you define these 2 operators in this way, so you should do a strict comparison here, right? So you should find the first key that is smaller, actually smaller than 28, and follow the right link of that, right? So if you are trying to find 28, you find this index entry and you follow this link here, right? And then you find the very last key that satisfies it is smaller than 28, and in this case it is 27, right? Then you find this index entry and you follow the link to the leaf page. And then in the leaf page, you can actually do a binary search, because here everything in the leaf page are actually sorted. So you can do a binary search, try to find 28, but you know, you find this point, but you do not find a match for 28, so you know 28 is not in the tree. And if you are searching for 29 here instead of 28, then you end up with the same leaf page, and when you do a binary search, you are going to find this data entry here, and you get a match for the data. Okay? That's how you do the search. And also you can do like range queries. You can try to find all the tuples that is greater than 15. So the way you do that is that you find, this is a little bit tricky. So you find the very first key that is greater than 15. Okay. So what you could do is that you can try to find the last key that is smaller than or equal to 15, and the next key would be just 15. Greater than 15, right? So basically, you are searching for 15, and you follow this link here, and you follow this link here, and you find 15 is actually in between these 2, and this is the very last key that is smaller than or equal to 15. The 14 is the last key is smaller than or equal to 15. Then you know, starting from the next key here. Starting from the 16 here, you know everything is larger than 15. And you do a scan of them. So you scan 16 and follow the next leaf page pointer to get to the next leaf page, and scan 22, 24, and follow the link here, and scan 27, 29, and so on and so forth, until you reach the end of the path. Okay? This is how you do the range search. And if you have an upper bound, like you are doing greater than 15 and smaller than 30, then basically you do an additional check where you are scanning the leaf pages. So once you end up here, the 33, you find that 33 does not satisfy the condition that it is smaller than 30, right? 33 is greater than or equal to 30. So that means basically your scan should end, because everything afterwards will be not smaller than 30. Right? That's how you do like two-sided range search. Okay, using the B tree. And so let's skip this analysis first. Let's first see how we do insertion and deletion. Okay. So how do we actually insert one data entry into the repository? The general, like this is a pseudocode for that. Basically, you do a search first. This is the search for the correct leaf L, leaf page L, and then you put that data entry into L. If L has enough space, then you're done. Okay. If it does not, then you need to split this L into parts, into two parts, and then one of them will have enough space for that, and you insert that new data entry into that particular page. And this actually can happen recursively because suppose you split up a leaf level page, then that means you need 2 pointers for those new pages, right? In your one level above. And in one level above, it can still like have no room for the additional pointer then. Then you need to split the the index page as well. Then once you split this index page, it ends up with one additional pointer to insert into the upper level. Then it can go like recursively up to the root until you split the root. Right? So let's see an example. So suppose you are inserting 8 in this tree here. What you are going to do is basically you do a search for 8 actually first. So you find the very first key, the very last key that is smaller than 8, and that means it's this index entry here. Then you follow the link, go to this leaf level page, and you try to insert this 8 into this leaf level page, but you do not have any space, right? So the next thing you do is that you first split this page. So you split this page into 2. You create a new page here, and this new page is going to be, so you copy over half of your keys entries into this. So basically you copy 5 and 7 here. It's going to be 5 star and 7 star. Then you remove this link and point the next leaf page link to here, and establish a previous link as well, and link this to the next page and do this as well. Okay. So basically, if you now your tree basically look like this is the first page, and this is second, and this is third. Okay. And since you have done this, you have room for the additional 8, right? So where do you put that? So you basically try to find a spot for 8, and it should be here, right? So you basically put this key 8 into the second page here. Now since you have split this page, but you only have one pointer in one level, in the upper level, so that basically means you need an additional pointer that points to the new page as well, and insert that into the root. The way you do that is that you copy up the smallest number in smallest key in your new page, in the right page, and create a new index entry called 5. Sorry, it should be a 5, not 5 star, because it's a column. Okay. So you create a new entry here 5, and with a pointer that actually points to the new page here. Okay. Then you will try to insert this entry into the root page. But the root page doesn't have any space, right? So you need to do this split process recursively again. So the way you do that is that you first create a new page here. Then you copy over a bunch of stuff here. That is, let me see. Suppose we copy over 17, 24, and 30, right? So I'll just first put 24 here and 30 here. Why is that? Because you only need 2 complete index entries to put 3 pointers, right? So basically, you scratch this pointer and point this to here, and scratch this pointer and point this to here, and there's one additional pointer here. So you scratch this one and point that to here. Well, what about the 17? Okay, so we'll show this later, but then we have space on the original root page, right? Because we have 3 empty slots. So then we can insert this 5 here. So basically that means this, sorry. This is a little bit messy. So you do not change this link, but you put a 5 here and point this link to the new page. That's how you insert the new page. Then move everything back. That's the only thing left is actually 13. So you put the 13 here, then point this link to the third page here. Okay. Then since you have 2 pages at the root level, that is not allowed. You actually need to create one additional level. So there you actually create a that's where you put this additional 17, right? Because if you insert index entry here, everything that's smaller than or equal to 17 is going to be on the left, and everything that's greater than or equal to 17, greater than 17 is going to be on the right. And you create these 2 pointers. Okay. Then you end up with something like this. This is the end result. Sorry, it was a little bit messy. So basically, you start your split here, then go up until you reach the you find some space there, or you reach the root. And notice one thing is there's one little tricky part of this process. When you do a split, if your split is on a data page, that means you are splitting something with data entries. You copy up the key, the very first key on the right page. But if you are splitting something on the index page, you do not copy up that particular number. Instead, you move up that particular number, that particular key. Does that make sense? So this is a copy because you have 2 5s here, right? But originally 17 was here. Then you do not actually put 17 on either of these 2 pages, either the new old page or the new page. Instead, you basically move this up to the new page up here. So this is copy up, and this is move up. Okay. So this is the distinction between splitting data page and index page. Yeah.
On the lowest level, if there was the key of 5, but there's multiple keys of 5 and they span both of the pages that you're splitting into and from, then
Right.
which do you copy on?
Right. You always copy the very first key in the right page, only in the page on the right.
Won't that invalidate the invariant that since there's 5s in the left page?
Yes. That would, as I said, here we assume we have unique keys, so you do not end up with that. If you do not have unique keys, like you can have duplicates, you cannot define something like this 17, so everything on the left is smaller than or equal to 17, and everything on the right is greater than 17. That's not going to work, right? Because you can have duplicate keys. So the way you do that is actually you define everything on the right is smaller than or equal to 17, and so everything on the right is greater than or equal to 17. Okay. Then you need to be a little bit careful where you do a search. Like if you search for exactly 17 and you want to search for the very first one, you need to make sure you always search for the leftmost match for that. And in sometimes, so suppose, let me give you an example here. So suppose this is a 16 and this is a 17, and you do have duplicates somewhere, right? So suppose your 17 can have multiple duplicates, and maybe I'm going to write this. So let me create a new slide. This is so suppose you have a page. suppose you have a page that looks like this. You have a bunch of 17 here. This is the data page. Okay. You also have a bunch of 17 here. 17, 17. So you have a 16 here, something else. And then you have an index page where you have a 16, and so suppose this is also 16, and you have an additional one that's say 15. Okay, and it's gonna look like this. So leftmost pointer points to the very first, and this is gonna point to the second, and you have a 17 here, and the third pointer points to the third page. Okay. So here the actual definition, so the meaning of 16 here is that everything on the left of 16 is going to be smaller than or equal to 60. Everything on the right is going to be larger than or equal to 60. And the same also applies to 17, right? So when you search for the very first key for 17, make sure you find the very last key that is smaller than 17. So you are trying to find some k smaller than 17, and k is the last one. So then you are going to end up with 16 here. Then follow the right link, you may or may not find some 17, right? Because like this can also be non-existent, right? But this is essential if you have duplicate keys. But if you do not have duplicate keys, then once you find the 17 here, you know it's gonna be on the left. If your definition is that everything on the left, everything on the left is smaller than or equal to the key, and right is greater than the key, right? If you are trying to find k and you do find k in some index page, you know that one is actually on the left, or it does not exist. And if you do this in another way, like I said, there are two flavors. You can do smaller than and greater than here, right? Then it's gonna be you're gonna search for a k that is smaller than or equal to 17, and it is the last one or the first one. It's the first one, right? And this changes to the first one. Right? So it's really tricky how you define this key range.
If you go back to the slide where we are like popping and moving,
Yeah.
So after 13 we have a space there, so why don't we just copy the 17 instead of moving it up? Like since there is a space now after 5 and 13.
Okay, yeah. So let's see why we don't copy it out from the index page. So suppose it's copied here. What should you put in the very first link?
After 13, I'm asking.
After 30, okay. Then let's see what should you put for this link? Right? You don't have anything to point to. That's why it's moved up instead of copied down. That's the key. Yeah, because basically that's because for each of these index pages, it has an implicit key at the very beginning. Okay, it's implicitly negative infinity, or the key actually as its parent. Right? So that's why you do not actually store that key. So I know this is a little bit tricky, but you cannot copy up the 17, but you need to move up the 17. Yeah.
We choose the 17th.
When you choose 17 instead of 24, that is because basically the way you do that is that you have to make every node satisfy that it is half occupied. So if you choose 24 here, this node is only going to have one key, 30. Then it's lower than half occupied. Right? So when you are choosing which one to choose, actually you need to decide where, you need to first decide where your additional entry is going to be inserted. Is it on the left or right? If it is on the, so basically the simplest thing I would do is that you write down all the keys you have. Basically here, you originally have 13, 17, 24, and 30, right? And you have an additional 5. Then you have 5 keys, right? And you choose the middle one. Always choose the middle one. Because you are choosing the middle one, and originally, because it was full, so you must have 4 keys, right? Then you have 4 plus 1 keys in total. And if you choose the middle one, you are guaranteed to have exactly this many keys. And this is guaranteed to be greater than or equal to half of your capacity. Right? So that's why you need to split it in this way. Yeah.
So now I'm wondering why this has 4 keys in class 1 and 2. Sorry, it says
Yeah.
4 keys, 5 pointers in class 2 tree and 3 pointers and 2 keys.
Yes. So let's see that. You mean why this has 2 keys and 3 pointers?
No, the total able to store.
Okay. Oh, so why it can only store this many keys and pointers?
Yeah, when the exam tree is.
Oh, that actually is just an arbitrary example. So this actually depends on system configuration, like how large the page is, how large your indexing entries are, how large the data is.
So the ISAM is not fixed at
Right.
pointers and keys.
Right. It's not. It's just an example. Why are you wanting this? So this is because you want to have a balanced tree. So suppose you do not have this condition. The same you could do is that you can have a equal list, something like this. So suppose your data is 1, 2, 5, 3, 4, 5, right? And you can have something like this. So put a 1 here, and points to here, and oh no, you put a 5 here, then you put a 4 here, then you put a 3 here, 2, right? And you end up with a very long list until you reach 1. Okay, and this is because you do not enforce the half-occupied the requirement, right? So in this case, the worst case you can end up with. So if you know, typically in a binary search tree, the worst case it will degenerate to a linked list, right? So this is the same here. Basically, you just have more links and more keys in one node, but still you can degenerate to a single list if you do not enforce the half-occupied requirement. So with half-occupied requirement, you can prove that this tree is guaranteed to have a log height, logarithmic height. Yeah. Actually, so we do have some analysis here, but I don't think today I have time to go over that. But this is guaranteed by the half competency. Yeah. Yeah. We have a few minutes left. Let me finish the division, and let's call it a day after that. Okay. So division is just the opposite of insertion. So basically, to delete something, you need to first find that, right? So the first thing is that you find that particular key in your tree, do the same kind of search you were doing in insertion or just normal search, right? Then remove the entry. It's a little bit different from insertion because if the key is there, you can always remove it, right? So you cannot end up with like it's full, you cannot remove the key, right? But the thing you can have that so the thing that can happen is that once you remove the entry, it becomes less than half occupied. Okay. So let's see an example here. Suppose you are deleting 19 here. It's easy. Basically, you just scratch it, and it is still half occupied, right? But what if then you further delete 20? Of course, once you delete 19, you should remove everything forward. Like it should look like this, right? And then once you delete 20, this page is less than half occupied. It only has one data entry here. So then you need to do a redistribution to ensure this page is still half occupied. The way you do that is that you can look at the next page, and you find that the total number of elements here, data entries here, are greater than the capacity of your page, or equal to your capacity of the page. That means if you evenly distribute the data entries between these two pages, each of them are going to be half occupied, right? So the thing you do is that you can move 24 to the left page, and this will be 27 and 29, right? This is called redistribution. So if you do that, you also need to copy out the very first key of the page on the right to its parent. So you're going to need to change the 24 to 27 here, right? Yeah. So another thing about this. So yeah, what if you you end up with here, okay? What if you further delete another key? So what if you delete 24 here? Then even if you redistribute these two pages, you still end up with at least one less than half occupied page, right? You only have 3 elements here. You cannot distribute them in a way such that each of them are half occupied. So the thing you do that is the way you do that is that you merge these two pages into one. Okay. So that's to say you copy over everything here. Okay. And then remove this page and link it to the next one. Then just deallocate this one. Then you will need to update the upper level here. So basically, once you do that, you will need to remove this link and this key here. You can remove this data entry entirely, so that the upper level only has one entry here. Okay. And since the upper level only has one entry here, it is less than half occupied. So you need to do this recursively. So basically, that means since this page is less than half occupied, and its adjacent page only has two entries. So in total, they have 3 entries. Even if you redistribute everything here, you still end up with at least one less than half occupied page. So you still need to merge these two. So this time, when you merge these two, you copy over this to here, and then you move. Since you will need to delete the index entry at their common parents, so you need to move this key down instead of copy, right? This is moved down, while this is like copy. Then once you do that, the root page becomes empty. That's not okay, so you just declare this is a new root. Okay? And scratch this old root page entirely. Okay? So then you end up with something like this. Okay? And still, you need to be careful about the process here. So basically, when you merge two leaf pages, you're going to copy out the smallest key on the right. While if you merge two index pages or non-leaf pages, you're going to need to move down the index entry in the text. Okay, it's the analogous of it's the same analogy to this insertion part, right?
Again, it cannot look like after the adjacent page, like since we were writing the leaf nodes, so we have like then we have 2 boxes, 22, 27, and then 29. We cannot like take from the last node to 33, 34, 38, 39.
No, you can. You can only do this in adjacent pages. Yeah, even if you can do that, like you go across one, right? But then you end up with a situation you still need to update that parameters because you are still one page fewer than before. Or like this. So even if you can look at 3 pages and redistribute them in a way such that all of them are half occupied, still you will need to update this index values, right? So this is not worthwhile for the purpose of like maintaining half occupancy because it complicates a lot to your code, to your algorithm. So that's why we only need to do either consider redistribution or. So yeah, I think that's the end of this class. This lecture. Okay, let's call it a day. And next time we'll continue with more C3 stuff. See you next time.
I do say, it's gonna be a busy weekend. Hopefully it's productive.
Everyone has talked about that. And I hope
That could get taught in Blue Up, is that what you're saying? Take that in Blue Up, is that what you're saying?
yeah. If they don't teach it, then I have to move
What are you reading now?
Yes.
Okay.
So
Yeah, it's.
at least you're not the
No, I'm so this is very high. Just not good for writing proofs. Two at least that works. You can mathematically prove it.
Yeah, that doesn't matter.
So
Only look at
good luck.
thanks.
yeah. So what we do has to only look at source. So when we try to find your
Hey. Yeah, let me.
Going.
So, your